Thank you very much, Philip. I have a feeling we are going to see your vesicles in some approved drugs by the FDA fairly soon. Yes, yes. Well, like you mentioned, you're using natural, readily occurring materials, and you're testing drugs that have already been approved in liposomes. So very, very, very interesting. Our next speaker is Dr. Chala Kumar, and very pleased to have Dr. Kumar fly up here from a much warmer climate. And I previously had met Dr. Kumar only indirectly, so it's very nice to have him here in person. Dr. Kumar obtained his PhD in synthetic organic chemistry from Sri Sathya Sai Institute of Higher Learning in Prashanthi Nilayam, India. And Dr. Kumar was a postdoctoral fellow at the very famous Max Planck Institute for Biochemistry in Munich, Germany. Currently, he is the group leader of nanofabrication at the Center for Advanced Microstructures and Devices in Louisiana. And I previously was just in a webinar with him from that location, so it's nice to be in the same physical place now. And he is also the president and chief executive officer of Magno Technologies. Dr. Kumar has authored over 30 publications, holds 10 patents granted or pending, and will be addressing us today on the following topic: magnetically modulated nanostructures in medical diagnosis, treatment, and tissue engineering. Please join me in giving a most warm welcome to Dr. Kumar.
Well, apparently the second slide has come before the first slide. Actually, I was just trying to analyze the previous speakers' presentations. I think one thing that's really struck me is that all of them talked about different designs for nanomaterial. So it appears to me as if there is a competition for who designs the best nanoparticles. So I'm really glad to be here in joining that competition, and hopefully Dr. Rothblatt would give us a prize at the end of the conference. So what I'm going to do today is to share with you some really exciting work that's going on the topic. It's a very exciting topic to me, which is magnetically modulated nanostructures. While I'm going to share with you what's going on in my own laboratory, I also would like to have a scaffold of information based on the research that's going on in the rest of the world. When I think of magnets, and I always think of the huge Earth, I think the place in which we are standing is a huge magnet. Earth is a huge magnet. Therefore, when you say magnetically modulated nanostructures, it's all very relative. The magnetic properties that we talk about are being compared here either with the micron size or the bulk size materials. Therefore, it's a relative to Earth. So when you look at Earth in comparison with the rest of the universe, rest of the galaxies, rest of the cosmos, so the Earth becomes probably less than a nano in size. So I think this is a very, very important point that we all need to keep in mind. It's all relative. Other day, I happened to go to a very nice cartoon movie with my daughter, Who Hears What? It's a very interesting movie because the story is all about a huge elephant which carries a speck of dust on its trunk. And who is there on that speck of dust? There are innumerable millions and millions of people living on that speck of dust. So the story is all about how that elephant saves that speck of dust from destruction. So I think it's all relative. Magnetic applications are relative. Magnetic field are relative. So the next important thing is to remember is beware of fake nano. I mean, we keep hearing nano everywhere. So we have, for example, nano iPod. Of course, commercially it's been extremely successful. Then you have nano shampoo. You have nano cube aquariums. I mean, you think of anything, people tend to add nano. Of course, you have the cheapest car on the planet, which is the Nano, Tata Nano. And on top of it, there are several companies who add nano as a prefix just to make sure that their IP goes up. So we have to be really beware of nano. But what I'm going to share with you today is the real nano. I'm going to talk to you about the nanostructured materials, of course, which have magnetic properties. And this is nothing new. We started making the nanomaterials in laboratory only recently, probably a couple of decades ago. But then nanomaterials and nanostructures have been there in nature for a long, long, long time. And looking at specifically magnetic nanoparticles, this is an excellent example to think of before I start my presentation. That is migration of several fish and migratory birds. They seem to have magnetic superparamagnetic iron oxide nanoparticles at the nasal. And that apparently seems to help them, guide them through several kilometer distances in finding their places. That's really amazing. So what I'm going to talk to you in this 15, 20 minutes of time that I have is, what are magnetic nanostructures and why are they unique? What is magnetic modulation? And what does it gives us? What kind of benefit the magnetic modulation gives us? What are the implications? And how this magnetic modulation gives us a unique opportunity in medical diagnosis, treatment, and tissue engineering. Then I move on to show you some excellent examples, excellent designs. Remember, I'm competing in this competition, so I would say it is an excellent design. So this design talks about integrated diagnosis and therapy. If you give me 1 more hour time, I think I would talk about the rest of it, but I'm not going to do it. That is truly important from my perspective because when we talk about nanotechnology and nanoscience, we are only envisioning some exotic techniques and tools which have no immediate applications in industry. But it's not really true. There are several nano tools and technologies that can be immediately applied in chemical and pharmaceutical industries. And that's why we have designed a concept called Innovation Box for implementation of nanotechnology tools. So when you really use this strategic tool to sort out various nanotechnology tools that are available, and you can really apply them into day-to-day activities like process development, product development in pharmaceutical industry. Okay. So why magnetic nanomaterials are unique? They are unique, simple. I'm not going to take too much time. They're unique because of 3 very important reasons. The magnetic nano properties can be altered. When you compare the bulk magnetic materials, in bulk magnetic materials, you have an opportunity to modify crystal structure, surface function, vacancies, defects, etc., in order to generate different magnetic materials with different magnetic properties. But when it comes to nano-sized magnetic materials, you have 3 additional components that gives us an opportunity to change or alter the magnetic properties. These are size, shape, and of course the composition. This second unique ability is that they can be conjugated to biomolecules. You can't do this with bulk materials. You can pretty much conjugate any type of biomolecule. You can conjugate DNA, you can conjugate peptides, you can conjugate antibodies, you can conjugate any organic molecule that you can think of. So that's the very unique opportunity that we have with magnetic nanomaterials. The third important aspect is that they offer multifunctionality. This multifunctionality can be obtained only with nano-sized materials, and magnetic nanoparticles offer an excellent opportunity in this aspect. So you can have control release imaging, drug delivery. Think of any feature that you need for biomedical applications. You can tailor your magnetic nanostructures and nanoparticles pretty much using this, this factor. So what I'm going to do is I'm going to give you a few examples how altering the size, shape, composition, is being utilized to solve a number of interesting problems. Let me start with the size, the influence of size. There's an interesting investigation that's been going on wherein people are trying to look at MRI contrast agents. For example, spion-based, superparamagnetic iron oxide nanoparticle-based contrast agents are very well known. But then, what is unique about spions is that they offer an opportunity to tailor-make contrast agents so that you can enhance the contrast depending on the tissue that you are trying to image, depending on the type of material that you would like to utilize for the contrast. So the first opportunity is to look at the size, influence of size. So different sizes of spions are possible to synthesize, and based on the different sizes that have been made, it's possible now to determine the optimum size that is really necessary for optimum contrast in magnetic resonance imaging of a number of tissues. Not only the size, you can also change the composition. For example, you have different types of ferrites that are known. All that you need to do is change the type of metal with these ferrites. For example, if you move from manganese, cobalt, or nickel. So these different types of ferrites have been synthesized, and an optimum metallic ferrite have been identified for contrast and magnetic resonance imaging. Now let's look at a very interesting concept that's being developed, which is the remote control of cellular functionality. I mean, if you look at cellular function, there's only one way that the nature does that. That is by using multifunctional ligands. What happens is the multifunctional ligands bind to several receptors on a particular cell, say for example, and the multifunctional ligands help in bringing the receptors closer, thereby triggering a cascade of reactions, cellular reactions. So the question is, can we use magnetic nanomaterials in order to trigger in a remote fashion such cellular functions? And there is a very interesting paper that's just came out in Nature Nanotechnology. The concept is, it's very simple and elegant. If you look at mast cells, which are actually the sentinels of immunoreactions. For example, if there are antigens coming in contact with the mast cells, these antigens are multifunctional antigens. Therefore, they attach to these different receptors on these mast cells and help them to come together. And once the receptors come together, they trigger in a cascade of reaction leading to increase in levels of calcium, which in turn leads to release of histamine. And that's what is responsible for your immune reaction. So what this remote control does using magnetic nanomaterials is you have an antigen, a single antigen directly bound to a single nanoparticle. And then when you have such a construct, when you inject them into these mast cells, what you would see is a single nanoparticle attaching onto the single receptors. So at that stage, really there is no cellular reaction at all. But the moment you apply an external magnetic field closer to these mast cells, which have already been bound with the magnetic nanoparticles, you see a agglomeration of these receptors happening on the top of the cell, thereby triggering the release of cellular activities. And that's a very cool example I can think of, really looking at trying to physically, remotely control the cellular functions. And that's possible with the unique properties of these magnetic nanomaterials. I also would like to share an excellent example. I mean, we are all familiar with gene therapy, and we have seen several examples and several approaches to incorporate design nanomaterials to enhance the efficiency in gene therapy. There is a serious competition between the viral vectors and non-viral vectors for gene therapy. Non-viral vectors have several advantages, and two of the most advantages are that they don't have cytotoxicity and they don't generate any immune response. But then the problem with the non-viral vectors is that their transfection efficiency is pretty low. So there are designs being developed, nanomaterial designs being developed in order to increase the transfection efficiency. And one such elegant design is by using a cylindrical shaped nanomaterial. These are all nanorods. And these are multifunctional nanorods simply because you have two different metals in a single nanorod. One is made up of gold and the other one is nickel. And the advantage in such a design is that you can have the plasmid or DNA on one metal, and you can have a targeting agent onto the gold surface. And such materials have been shown to increase in transfection efficiency, and they have been extremely successful in gene therapy. Yet another example is development of implantable sensors, again using magnetic nanoparticles. These implantable sensor chips for cancer biomarkers are being designed based on a simple concept of what is called as magnetic relaxation switches. So the concept is when you have a magnetic nanoparticle, it has a certain amount of relaxation. So for example, T2 relaxivity. But the moment this magnetic nanoparticle comes in contact with another magnetic nanoparticle, it changes its relaxivity. And this change in relaxivity is quantitative. And that's what is being utilized in development of implantable sensor chips. And what we see here is a sensor chip made up of silicon substrate, and then you have an alumina semi-permeable membranes. And within these, you have these magnetic nanoparticles bound to antibodies of, say, for example, cancer